Thank you. Thank you, Eileen, and thank you, Colorado School of Mines, for inviting me here. It's kind of payback because I tried to get you to Cal State Fullerton during your Darcy lecture, so I appreciate it. I am the 2009 McEllhiney Lecturer for the National Groundwater Association. As probably many of you know, they have two lecture series, one being the Darcy Lecture and one the McEllhiney. The McEllhiney is a little bit different in the fact that one of my big things is to go out to all the drilling contractors, groundwater shows across the nation, and actually got a chance to go to Panama as well to talk to the South American Drillers Associations. So there's going to be a little bit of practical stuff associated with this talk, as well as some of the science that I've been using associated with boring logs. So with that, we'll go ahead and get started here. The McEllhiney Lecture Series is named after William McEllhiney, who was the original founder of the National Groundwater Association. And what made him unique and what makes this kind of lecture series unique in my mind is he was an engineer as well as a water well driller. And you typically don't get that, and you certainly don't get a lot of that today. And so he really brought and started NGWA under this idea of trying to bring science with the manufacturers, suppliers, and the contractors all together under one umbrella. And that's one thing that makes NGWA very unique, and something I've always enjoyed about is because when I go to their conferences, I'm talking to a guy who actually makes the sampling device, to the guy that uses it, to the person such as myself and like you guys who actually uses the information and the data that's collected during that. You just don't get that in other associations. The other thing is his big idea about NGWA was to be a clearinghouse for all the information associated with water wells, hydrogeology, both science and the practical use of it. And I think that's something that still lives today, and certainly something I think NGWA tries to promote. I want to thank Franklin Electric. They're the ones that are sponsoring me to go around the nation and talk this year. I still have about 10 talks to give, and I've given somewhere around 20 to 25 already. It's been a long year. But they have been the sponsor and underwriting this lecture series since 2000, and are actually signed up through 2010. You can nominate yourself to be the lecturer for this thing. I did not, so I don't know who did, whoever it is, but I did not try to invite myself to be this lecturer. And in fact, the topic that I'm going to talk about today was picked actually through, they asked me, here, give us 5 topics, and I gave them 5 topics. They actually had a committee, and this is the topic they picked, which surprised me. It really wasn't the one I expected to be giving, but it is one that they thought was something that was worthwhile to try to present and try to get some of the information out there that I'm going to talk about. So I'm going to go through some definitions, importance of the topic. I'm going to give you some examples, some good examples of boring logs, and some really lousy ones that we'll have a little bit of fun with. We'll talk about what can be done to improve, which is always what we're trying to strive for, especially with the students in the audience. And talk about some of the present research I've been working on for the last 5 or 6 years in the Mojave Desert. And then what's the future hold as far as logging wells? And there's actually some fun things I think we can talk about, and I think are going to start happening and we're going to start seeing. So one of the things I want to talk about first, though, before I move to the next slide, is why should anyone listen to me when it comes to talking about drilling logs? Well, as it turns out, as a graduate student at Western Michigan University in Kalamazoo, Michigan, they have their own drilling rig. And they found out in my first month I was at the graduate student there that I ran fork truck during the summer working at 3M. And so they invited me out and said, oh, by the way, since you drove fork truck, you can certainly drill a well. So the next thing I know, I'm running a drilling rig. Now, as a drilling rig, we were able to do hollow stem down to about 100 feet, mud rotary down to about 200 feet, some direct push off of it. It's a pretty unique little toy, essentially. So there's certainly a putt-putt rig. But I got a chance to put in 400 to 500 holes every single year I was in graduate school. And so we got to go play. I mean, isn't that what graduate school is supposed to be all about, is going to play? Well, I got to play. Me and 2 other guys, or a couple of girls, would just go out and start drilling a hole. And we'd drill the holes good. We'd drill them bad. We'd try different things. We just tried all kinds of things. Our job was to learn. And so from that, I got a pretty good handle on actually how to drill. And in fact, during my tenure in graduate school, I actually did all the drilling for all the graduate students on campus. And we had somewhere in the neighborhood of 100 hydrogeology masters and Ph.D. students at the time I was there. So we put a lot of holes in. What allowed me to do that is the state of Michigan, unlike many other states, does not require a driller's license for monitoring wells. Okay? If it was a drinking water well, you had to have a license, but any Tom, Dick, and Jerry could actually go out and put a monitoring well in. So I was allowed to go do that. And so I did. And so some of the lessons I'm going to talk about today were some of those lessons I learned back then. And then the other thing I've been doing over the last 15, 20 years has been looking at other people's boring logs. And I have now in my database somewhere around 150,000 boring logs from around the world that we've databased and try to look at them and see if we can see some things that are good about them and some things that are bad about them, and see if we see some trends and other things. And a lot of that's what we're going to be talking about here. So, definition. Boring logs, driller's logs, water well logs, e-logs, what is it? They're all basically the same thing. They're a piece of paper that tells you what happened on site. What happened? What did you find? What did you drill through? What were you drilling for? Who did you do the work for? It's basically transferring information you collected on site to some other end user you may or may not know. And so basically the log describes what all that information was. So why did we create them in the first place? What's interesting is I just got a call actually yesterday from the state of California asking me if I had any historical information on why people even started producing logs in the first place. Because they had heard I'd been giving this talk, and they called up NGWA and they sent them to me. Well, as I told the guy, I don't know why they started. You know, it certainly makes a lot of sense that if you're going to do all that work and spend all that money, you should produce something for it. And so maybe that's the reason why. It may be just a reason for someone to track all the different things they were doing because their memories are like mine. They couldn't remember what they did yesterday, let alone what they're going to do tomorrow. So basically, logs are generated for a lot of different reasons. They're private municipal industrial water wells, very commonly done. Environmental wells. We even do boring logs for soil gas wells where we don't even touch water. We do them for geotechnical borings. We even do logs for trenches for fault and seismic activity like we do in Southern California. Oil and gas exploration. Obviously, they spend a great deal of money in working with those logs and produce these really fancy, expensive logs all the time. Much different than we do in the environmental or water well business. Dewatering and injection. We do them for all those different purposes. But remember, well logs are more than just that piece of paper. Okay? The information that's on there is very, very important and something we should always pay attention to. So logs contain a lot of different information. Hopefully they have all this information, but as you'll see, many logs don't have even a third of this information on them, which makes them less useful. Location. I would hope that the location of where you put that hole was actually on the log. It isn't. In the old days, before we had GPS, most logs were actually based upon a quarter section. So you end up having 30 logs for that quarter section. Well, they all plot in GIS as one point. So now you get all these different geologies that cover, you know, a big section, but they all plot in one spot. So we're trying to get that better. Type of drilling is a mud rotary, air rotary, you know, bucket auger, cable tool. Types of sampling, if you collected any at all. And a lot of times we certainly don't collect enough data for that. The depth. You would think that putting the depth of how deep you went would be something fundamental and put on every log. It is not, as we've learned. Geology. Okay, that's one of the things we're going to talk about today is trying to figure out how we can do some better ideas on geologic sampling and classification. But geology isn't always done to a level that you guys would probably do in a classroom or on any job you guys would be working on. Geophysics, if you get a chance to run geophysics, absolutely, it's always great. It confirms your geology. It's a continuous log versus having spot samples every 20 or 30 feet. Depth of water, during and after the well installation. Those can be two very different numbers. They can have a whole lot of information that you can derive from them that can help you with some interpretation down the road. And chemistry if you need it. Now, a lot of states mandate for the water well business, before you can actually put the water well into service, you have to take a nitrate test. Not every state does that. Some other states, they look at some other constituents. I don't know what the rules are in Colorado, so maybe you guys can enlighten me on that. So, why should anybody care and why should anybody in this room even listen to me today? Well, you only get one chance to collect that data. And this is something I really want to emphasize to the younger people in the crowd. You're out there doing a job. Your job is to log that hole. You only get one chance to drill that hole the first time. You don't get another chance, so why not you do it the best you can. You have an ethical and a legal obligation to do it correctly and to do it to the best of your abilities. Data will outlive you and the boring. Okay? It's something to keep in mind. A lot of the boring logs I'm looking at in the Mojave Desert are from the turn of the century. That well is no longer there. The people that drilled it are certainly long gone. The companies that were associated with it are long gone. But yet here's a piece of information that I can use to start interpreting the subsurface geology in that area and ultimately come up with some hydrology and hydrogeology impacts to that geology. So this is something to keep in mind, something I never got when I was a grad student. I did a cruddy job of doing logs. I mean, put in all those borings all those times, and they finally came back to me after I was gone for a while and said, do you have all the logs for all those wells? Do you even know where all those wells are at that you put in? I said, well, no. You know, so there again, the project certainly has outlived me. The other thing is future decisions are going to be based upon those boring logs. Okay? And what's important about this is, remember those logs I was talking about at the turn of the century out in the Mojave Desert? Last year, actually probably 18 months ago, I had a call from one of the local water agencies asking me for some subsurface geology information in a particular area where a 22,000 home development was getting ready to go in. Well, they needed to find out what the depth of water was, maybe what some of the geology was, and some other information from what I could gather out there, so they can get their loan on a 22,000 home development. Now we're talking, you know, hundreds of millions of dollars, maybe low billions of dollars, and they're basing it upon information that was collected in the turn of the century. Now ultimately they are going to have to drill new wells, that put in production wells and everything else, but their first cut to see if they go further was from information from 100 years ago. So decisions are going to be made upon this. The other thing that happens routinely in the environmental business is you do these monitoring wells, there's going to be a remediation system put in that may be worth millions of dollars or at least hundreds of thousands of dollars. It's going to be based upon your work in the field. So if you did a cruddy job, what kind of decisions, what kind of future business decisions may be based upon that information? So why is this good for business? Now remember, I'm usually giving this talk to water well drillers and environmental drillers and geotech drillers, so bear with me a little bit here. But basically, we have a professional and an ethical obligation to put down the right information to collect that information the best we can. And if you have a license and you're a licensed geologist anywhere, does Colorado have a licensed geology system? So there again, as a licensed geologist in Colorado, you have an ethical obligation to put down the right information. I think it can actually help your bottom line, because by gathering the most information you can and making it good, you can make better decisions down the road. Rather than putting in another monitoring well just because the last guy put in a lousy one, that costs money somewhere down the road. And so there again, I think we can, by keeping track of information and whatnot, we can actually help our bottom line. And then you can actually, you know, by doing better well logs, actually use them for some marketing purposes. Remember there again, keeping in mind the water well business. To prove that I actually drilled a well, here's me back in the younger days before I had a belly. And obviously Michigan can get cold, so. It seems like I was always drilling when it was snowing outside. You know, I couldn't drill during the summertime when it was nice. We always had to drill where it was really cruddy weather. And this one happened to be on a pig farm, and we were drilling right next to the waste bin. So it was mighty smelly, and it's dry. We had 12 inches of snow before I was done drilling the first 2 monitoring wells. So it was a lovely smell and cold. So, nonetheless. Huh? They tried to stay away from us. We're a little loud, yeah. And then plus I'm some grad student out there drilling a well. They didn't know what to make of me. That's for sure, yeah. At least I have a hard hat on in this picture, so that was good. So, some examples. And these are the not so good examples of logs I've found over the years. And I had to basically go through my system and actually find some that were politically correct. There are a whole bunch of well logs I have that are not politically correct. So I try to pull the more fun ones and the ones that are maybe politically correct. But 90% of the well is granite. Now, if you're a student, you're trying to do a cross-section and you're using this well log, how are you going to do that? Okay. This one down here has clay with a sandy layer and water over that 155 feet. So where is the water? And is it a sandy layer or sandy layers? You know, it would help to know that if you're trying to do some cross sections across there. Here we have 30 feet of first water. It's a pretty big first water zone. Usually when you hit the water table, it's should be closer than that. Here's lava rock. That's one of my favorites. So is it basalt? Is it a tuff? Is it igneous? Or is it some kind of obsidian flow? What is it? We don't know. And then down here we have the usual sand and granite, which don't typically mix in geology. Okay. And I'm sure everyone's had Geology 101 in this room, so probably something we shouldn't see. The other thing you notice is granite spelled multiple different ways on here. So spelling certainly is something that we need to work on. Here's 655 feet of alternating layers of decomposed granite and hard granite. Now, if I'm trying to do trying to figure out information on groundwater, I'd like to know which of those two it is and where. Not that the whole log is that. Then my favorite here, we have 80 feet of about the same material. Okay, now, I don't know where that geologic description came from. I've been trying to read books and other things on it, and I've talked to many people, and I still haven't found that geologic term yet. Now, this guy over here did a really good job describing it. They described every 5 feet. It's pink, it's gray, it's brown, it's purple, it's black and white, it's gray and white. I mean, they were definitely not colorblind, and they did a great job of doing the colors. Okay? But probably overdid it, because we probably didn't have that many color variations within that hole. So some better examples. Now, these are probably done for environmental purposes. And in fact, this person here actually took and plotted the blow counts, the geotechnical blow counts they were doing. Well, that's great. That gives me some more information, right? It tells me some of the stiffness properties of the materials that I'm going through. If I'm going to put a parking garage on top of this, which I'll talk about in a few minutes, I would certainly like to know that information. They did a pretty good job of describing them here. The other thing they did, which I really like and I think that we should try to strive to do on every log, is put a picture down. Put a picture of what you put down in the ground. Why? Because people learn in two fundamentally different manners. Half the people in this room can read something and picture in their mind what's going on. The other half in this room can see a picture and put words to it. In order to teach to the whole, you need both. And so why not have a picture sitting there showing me that here's my screen interval, that I had some extra screen or extra drop pipe in the bottom of the well. Where did I put the grout at? Did I actually put a seal in there? This one over here shows me how deep we drilled and exactly where we put it. And somewhere in there they actually have where the water table's at. So why not put a picture on there? And then you can get to these. Here's one of the best examples of well logs I could find anywhere, and of course it's the one I did. So of course it has to be the best. Okay? One of the things we have on campus, and this is at Cal State Fullerton, and if you don't know where Fullerton's at, it's Cal State Disneyland. Disneyland is 5 miles away and started exactly the same month and the same year Cal State Fullerton was created. We also have big white boxes for buildings, unlike your nice campus you have here. So the running joke is Cal State Fullerton was built out of the boxes that Disneyland showed up in. So, but nonetheless, we have a 1,000-foot groundwater monitoring well on campus. And I'm contending still today that is the deepest groundwater monitoring well on a campus anywhere in the world. Until someone tells me differently, unless you guys have one deeper. But we actually have, it's a West Bay well, and it actually has 6 sampling ports on there. So you can actually see here where we have 2 different screen intervals. We describe the geology, obviously, to the nth degree, because we got students who can spend hours and hours doing this. They're not getting paid usually. And then we put the geophysics on there. And then we have nice header information up here describing all that stuff. And then we also went through one step further and actually put a color-coded geology strip log in it. So we can actually look at this in multiple different ways. And certainly this would be something nice to see on every log, which is unreasonable, of course, but certainly something to strive for. So, some of the software you can use for generating logs. Well, remember, there's all kinds of software out there, and there's software coming along all the time. The software we use at Cal State Fullerton is LogPlot by Rockworks, but you can use Excel. You can use Borehole Mapper or Statter here, or Petra. Petra is the $250,000 well logging generation software for the oil industry. But who's going to spend $250,000 to make a boring log? But somebody does. And then I did a talk at somewhere back east, and some young kid ran up to me immediately and said, "Oh, you don't have my software up there." and yelled at me. So I had to put his software up here called QuickLog. But nonetheless, there's a bunch of software out there that makes it easier to produce some fine graphics and actually produce some logs based upon the information you collect in the field. But remember, great software is never a substitute for that good data collection in the field and good field notes. So, how can we improve? Well, looking at these logs over and over and over again and trying to do some geologic modeling with them and some hydrogeology modeling with them, some of the things that came across with that, as well as my field experience in the past, is we can certainly improve on sampling. And what I mean by that is, the driller spends between $500,000 and plus up to $1 million or more than $1 million in this nice, pretty drilling rig. Okay? We spend tens of thousands of dollars to put the monitoring well in, and yet, what do? We send the cheapest person from the office out to collect the data, and we take a $5 sample with a split spoon. So where's the weak link in this system? It's our sampling. We don't do a good enough job in it. So certainly that's one place we can improve on. The other thing I contend is our descriptions are all over the board. Okay? I have somewhere in the neighborhood of 5 million different descriptive terms people have used for subsurface geology. Now, luckily for us, there's not 5 million geologic units that we should be worried about, right? But yet somebody's invented some new terms, and so we got to do a better job of consistently saying the right thing for the right term, and maybe one of the things I want to promote here, actually just simplifying it and coming down to a simple classification scheme. The other thing is we can pull up more information that we're not putting on those logs, and one of them is, if you're doing a mud rotary rig, is anybody actually taking the mud weight and mud thickness that's out there? Something that's routinely done in the oil and gas wells is never done for environmental or geotech or water well business. So why not take that information? Because it tells you something about the lithology you're going through. Are you making water? Are you losing water? It tells you what's going on downhole. And remember, the hardest thing about this is we can't see what's down there. We're trying to interpret what's down there. The other thing is, if you've been around a drilling rig at all, did it chatter a little bit? What I mean by chatter, did it shake? If it's shaking, you're going through some gravels or at least some cobbles. And so why not write down what depth that was at? You may not get a sample of it, but why not write down that information? Then location. There's no reason why we can't go down to Walmart and get a $60 GPS unit and at least get our well within 20 feet. Okay? There's no reason why we have to go back to a quarter section. Anybody can afford it and anybody can do it. Now, what's nice is, having gone to all the different states around the country, most states are starting to require it for all wells that they're surveyed in with at least with a handheld GPS. And you actually have to turn that in with your log. So that's good news. We're actually heading in the right direction. And we can improve on it and try to get better with it. So, with sampling, there's a whole host of ways we can sample geology in the subsurface. We can take cuttings that are just coming out of the hole as we drill down. We can take split spoons like we see here, where we drive a sampler in the ground, we measure the blow counts, which is how much it's hit, to drive, how many times you have to pound it with a 140-pound hammer, the 30-inch throw, to go 1 foot, and you plot it out. And then you bring it up and you try to log what's inside of it. You can put the samples in rings for laboratory analysis. You can run permeameters on it, all kinds of different things. The Shelby tube. If you're in an area that has a lot of clays, people will use Shelby tubes. So what's a Shelby tube? Probably not many people have even ever heard that term before. Take some irrigation pipe that you see out and about in the farms. 3 or 4 inch diameter aluminum irrigation pipe. Hack it off in a 3-foot section, file down the end, and you drive it into the clay and you pull it back out and you got this nice clay core. You can take rock cores like we've seen here. Simulprobe. Simulprobe is another one of those kind of inventions out there that combines a water sampling tool with a split spoon tool. It can also take soil gas in the Vado zone along with a soil sample, but it takes it simultaneously at the same location. Now, if you're trying to do any natural attenuation studies or trying to do some remediation alternative designs, sometimes you want to actually get pore water from the formation surrounding your core but not degrading your core. That device would allow you to do that. Also, you can use balers, which they use off of cable tool drill rigs. Here's one of my students standing in the yard of Lane Christensen in Fontana, California. I don't know why you would use a 30-foot tall, 5-foot diameter baler, but somebody must have used it one time or another because they're standing there, and he really wanted to have his picture taken. And this row is probably 100 yards long of these balers just lined up. It's pretty impressive, but they don't move much. And then the other thing is drilling speed and down pressure. There again, something the oil and gas industry uses routinely, we don't typically pay attention to in the water well, environmental, or even the geotechnical business. Once again, why not take a look at that? So we have a whole host of sampling ideas here, but we don't really take advantage of them, or we take advantage of very little of what the information we could collect from each one of these. The drilling techniques. The other thing that comes up is we have a whole host of sampling techniques. Well, they're associated with a whole host of different types of drilling. There's a reason why one type of drilling rig does not exist. There's a whole bunch of them. Why? Because we have different geology we're drilling through. We have different purposes, as we've seen and talked about. It's a whole host of things and reasons. So we have rotary, direct and reverse, hollow stem and solid stem, direct push, the geoprobe type things, they're AMS. Cable tool, one of the oldest drilling technologies known to man. It's still a great one. Everyone complains, oh, it's slow and it's loud and blah, blah, blah. It's a great way to put in a water well, and it's even better for environmental purposes because I can seal off the formations as I go, and I can sample every millimeter or every centimeter if I want to take it that slow. And I've actually done some of that stuff on landfills. Sonic rigs have come about here recently. It's not really new, but now they finally figured out how to make them faster and better, and it's great. It's a geologist's wet dream because now when you drill, you get a core of the alluvium that's 6 inches in diameter for the whole thing, and they can lay it out on the sidewalk. And in fact, I was just out working with an environmental firm in LA, and they have basically a giant strip mall. We actually laid the core out on the pavement and put them and lined them up, and we just did our cross-section right there in the pavement with the core laid out. It was beautiful. It was a great way to do it. Then we'd subsample what we needed to. Directional drilling is a lot harder to do samples with, but it's certainly very important when you're doing horizontal or directional. Then don't forget the hand auger, our best tool, right? Everyone should have to do a hand auger hole before they graduate. It's actually one of my mandates for my hydrogeology students at State Fullerton. Take them out to the backyard and just say, hey, start digging. So here's one of the wells that me and my students drilled out in the Mojave Desert. It's a 4,000-foot monitoring well for the Mojave Water Agency. It took us a month to drill that. It only took us 2.5 weeks to drill the well I did on campus. And we drilled 24/7, so we had to go on shifts, which was interesting in itself. And then here's on campus where we did some hollow stem auger drilling rigs. So the reason why we have so many different drilling technologies is because we have a lot of different reasons. We also have a lot of different sampling technologies tied to those. One of my pet peeves in talking to drillers out there is they always go, well, I can't use a split spoon off of a sonic rig. Why would I do that? I said, well, yeah, you can. In fact, I've done it. Why would you want to do it? Well, maybe I need the geotechnical information that I can't get from the long core. I need those blow counts. Well, go ahead. When you pull the core out, go ahead and send a split spoon down there. There's a way to mix and match these things, and they'll complain a lot, but they can do them all. In fact, the cable tool guys always complain, oh, I forgot the split spoon back at the shop. I can't do it today. I said, it don't matter to me, go get it. So you can actually make them and talk to them. They don't like it, but you can make them do it. And so you want to be able to compare and contrast and put the right tools from your toolbox on the job for the right reasons. Our campus, of course, has palm trees. I didn't see many palm trees around here, so that's what that one's for. And this is in Malibu, which is another fun place to drill. So one of the things I want to talk about is sampling and sample classification. And I think we can do a better job in classifying things by doing a few simple things. One of the first things we got to talk about is there's two types of data we're going to collect in the field. There's going to be permanent data and there's fugitive data. Permanent data is like the well location. Okay, hopefully that well is not going to move too far. So if I don't collect the GPS location on it today, I can go back in a week or a month or 6 weeks and actually collect that information and put it on my log. The fugitive data, on the other hand, I pretty much got to collect it right then and there. And one of the good examples of that is soil moisture. You can't take your samples back to the lab, sit them off in the corner, let them dry out for a month, and go over there and say, oh, the soil moisture is 0. It doesn't work that way. You got to collect that information pretty quickly. And so you got to know how you're handling that kind of data. So when it comes to classification, one of the things I'm going to promote is that we use the Unified Soil Classification System, which is developed by the BLM and the Corps of Engineers. What's nice about this is you can download what's called the Earth Manual from the internet. If you just type in the Earth Manual in Google, you can download this 1,000-page document on how to describe samples. Okay? Now, I don't think there's probably too many people in this room, even the professors, are going to read the 1,000 pages that's in that book. Okay? The good news is, for the students in the room, is there's only one page you have to worry about. So out of that whole 1,000 pages, there's only one page, and it's this page right here. And this page describes and lays out the soil classification system that the USCS is based on. And what it's based upon is grain size. And certainly grain size is a much easier way in alluvial sediments to characterize your sediments. And it also helps you because now, based on grain size, I can actually make some permeability and porosity calculations from it. And so there's a lot of tools and things for this. There's some geotechnical gauges, which I have, and I would move, but they don't want me to move from here, that actually are nice little plastic things you can take to the field, has cheat sheets on it. So you can, this is pretty simple to do, you can do it quickly. My students, actually starting next week, will be doing every 5 feet of that 1,000-foot log I have on campus. They're going to be doing classifying every 5 feet of that. Okay? By the end of it, they're going to be able to look at it and throw it away in a matter of seconds and actually classify it and actually be routinely pretty good at it. There's actually a manual that NGWA has and sells that someone wrote that tells you, it's like 10 pages, tells you exactly how to go through what I'm talking about here. So, in order to know about grain size, we have to know two terms. And hopefully everyone in this room has probably heard grading and sorting. Well, for those who haven't, the easy way to think about grading is this. Cal State Fullerton mandates that I grade my class based upon an equal distribution of grades. Not a bell grade curve, but an equal distribution. In other words, if I give 5 A's, I have to give 5 F's. I give 10 B's, I have to give 10 D's. And then C's and C's in the middle. So I have to have this nice equal grading situation. So a well-graded soil is one that's going to have all these different distribution of grain sizes within it. Now, a poorly graded class is one in which I give everybody C's. Okay? And so a poorly graded soil is going to be one that has all one size of grains, i.e. beach sand. Beach sand by nature is bimodal. It only has 2 primary grain sizes. And so by nature is a poorly graded system. Sorting is the opposite. So if I have something that's well graded, it's going to be poorly sorted. Same is true if I have something poorly graded, it's well sorted. So the unified soil classification system is not only based on grain sizes, but whether or not something is well graded or well sorted. So if we go back to our unified soil classification system, it breaks it up into 2 halves. Sorry. We have our coarse grain material here, where we have our gravels and sands, and down here we have our silts and clays. Now, what the tough part about this is usually most people get the sands and gravels pretty quickly. That's easy. But how do you tell the difference between silt and clay? Okay? So how many people in this room, how do you actually determine that? Well, you can always go back, because everyone in the Colorado School of Mines probably has a lab that has a sieve analysis in there with a laser refractometer that tells you exactly what the particle size is for the sample. Well, probably no one has that in the real world out in the field. So how do you do it? Well, sit there and one of the tricks you do is you roll it out in your hand. Is it friable or not? Can I snake it out into a long snake? Or does it start breaking apart in pieces before I get there? The faster it rolls out, the longer it rolls out, the more clay content I have. Starts breaking out, or is more friable, the more silt I have. The other thing is you can always take it and put it in your mouth. If you can feel grits, it's silt. Can't feel any grits, it's clay. Problem is, if you're on an environmental site and you have a lot of gasoline, probably not the wisest thing to do in front of the regulator anyway. So that's probably not the trick you want to use. But the old guys, that's what they might do. One of the tricks I was always taught was you roll it out and you make a little person out of it. And you hang them by their neck. If the body separates from if the head separates from the body, it's more silt than clay. The problem is, if we make an overweight person, it's probably going to skew it a little bit. If I have a skinny person, it may skew it the other direction. So not highly scientific. Other tricks people use, put it in a little 40 milliliter vial with some water, shake it about, let it sit on the side a little bit, come back and see how it graded it out, how much silt might be in there. So there's some tricks you can use in the field, and they all come about, and you can probably come to it. So then the question is now I've figured out what the silt content is, how do I determine if it's an organic or inorganic clay in the field? Really, the only way you can tell the true difference is to take it to a lab. But I'm contending for most of the times, can you just tell me it's a clay? Yes, you may have some odors sometimes. You may find some fibrous material in it, so you can tell it's an organic clay. But most of the time, you're probably not going to find that. So why not just go ahead and tell me it's clay? So I'm not so worried about this bottom part down here. Just tell me, is it clay, is it silt? Make the changes up here so you can tell me what they are. You also notice over here an SW, for example, is a well-graded sand with fine to coarse sand in it. So that should be something you can quickly kind of fill. Now the other trick is, and because we're always geologists, so we can want to make things more complicated, is we can actually call it an SW with a little ML in it. So we can start mixing and matching these things, but really that kind of defeats the purpose again. We just want to keep it simple, so I have something when I start doing those cross sections that I'm modeling that I can compare equally across the place. Because what is a silty sandy gravel with a trace of boulders and cobbles? I don't know what that is. Okay? So nonetheless, that's where we're trying to head towards. So try to classify the soils based upon the Unified Soil Classification System. What about color? Okay, we can always go buy that $150 color Munsell chart, and probably everyone has sitting one somewhere, probably collecting dust, because how many people really know how to use it? Is it in the sunshine? Is it a cloudy day? Am I under the truck in the shade? Did I spit on it, or did I use DI water? You know, all those things can actually change colors just slightly. So if I'm doing wetlands, yeah, I want to make sure I know what those wetland soils are like, or is it modeled? But if I'm doing most of the stuff, just tell me, is it tan, is it red, is it black? Keep it simple. Go through the silt stuff. Obviously, you can do some things in the field, but most people are not. You could do toughness tests and dilatancy tests, putting your penetrometer into the sample and see how much it goes into it, all kinds of things. Sands and gravels, one of the things we have to worry about is angularity. Why would I have to worry about angularity? Well, if I'm doing a rotary type drilling with a trichome bit, and all of a sudden all my sediment coming out of the rotary tank is all the same size. It's all a coarse sand. Well, I'm looking at it and I go, well, it looks pretty angular. What's that tell me? It tells me that it was bigger. I took something that was bigger and I broke it up into something smaller. So now when I do my grain size analysis, that's not really telling the whole story. I know it's something bigger. I don't know how big, but it's definitely bigger than what I'm seeing in my hands. So something you have to pay attention to. And you got to pay attention to, is it a fresh cut or fresh fracture on it, or is it something that's older? There again, just some things you have to pay attention to that most people do not. Oversized material you're going to find in cable tool wells and stuff, so there again you can work with them pretty easily. Cementation, how many people take acid to the field? Well, everybody in school always has the acid bottles with them. As soon as you get in the practical world, ask an environmental consultant how many times they take an acid bottle to the field with them. They don't. You know, I had a water well driller from Pennsylvania. He says, yeah, I do all the time. He goes, I have an eyedropper and I go up to my battery and I take some of the water out of the battery, it's acid, and I put it on the rocks to see what the cement is. I said, that's a wonderful idea, except you're going to drain your battery sooner or later. But nonetheless, that's what he used. But certainly we can look at the cementation type because I can tell us some more things. Certainly when we're trying to look at permeability and other things associated with hydrogeology. So take your sample, you put it out in your hand. I apologize. I did have, when I started this lecture tour in January, I had all these nice little trays set up that I was going to bring to the classroom and hand everybody so they can actually touch and feel this. Little did I know that Homeland Security will not let you take soil onto the airplane. So they confiscated my first set. So I said, okay, tried it at Orange County John Wayne Airport, let's try it at LAX. They confiscated it there too because I didn't have a certificate proving that the sediment was clean. So I don't have any dirt with me, so I gave up on that pretty quickly. I know, the things we have to deal with. Nonetheless, so you just basically lay it out in your hand, figure out the percentages, put it in the classification, throw it away, mark it on your log. And once again, keeping your coarse stuff up here and your finer materials down here. Not having to worry too much between these two. However, I want to warn you guys, something I forgot. I've been teaching soil classification both in field courses as well as the classroom for 20 years. I'm good at it. I can teach anybody within a half an hour to classify all these soils, and routinely then they'll get what I consider be right all the time. And I was good at it, really darn good at it. And I actually had my students going out, and they were the people hiring them thought they were great at it. Well, I had a student who actually was there before I started at Fullerton, and took him 6 or 7 years to get his undergraduate degree. Okay, full time. Okay, he's slow. He's a big guy, probably 6'4", just call him Big Joe Rowe. Oops, probably wasn't supposed to tell his name, but nonetheless. And he graduated from school. He was happy. He got his first job. And since I made him go get OSHA training while I was in school, he was able to go out on the job within the first couple days. Guess where his first drilling job was at? After all those years of trying to get away from Cal State Fullerton, he was back on campus drilling wells for a new parking garage we're getting ready to put in. Okay? And of course, the parking garage is going on the faculty parking lot, so my parking lot got pushed further away. So they're getting ready to build this 5-story parking garage there, and he's out there, going through, logging all the samples. So I went up to him and said, "Hey, Joe, how's it going?" He's doing great. I can't believe I'm back here. All these years I've been trying to get away. I said, "So what are you drilling through?" And he goes, "Okay, it's an SM, and then we had a little bit of SP and stuff." And I got kind of puzzled. I said, "No, what are you drilling through?" He goes, "I just told you, same material as above." No one's got that joke in 20 talks, by the way. Nonetheless, I go, "No, what were you drilling through?" And he just got this puzzled look on his face. "I told you, this is what you told me to describe it as." What I forgot to tell him was, put it in context. He wasn't being a geologist. Were you drilling through an old gravel lag? Were you drilling through an old stream channel? Was there an old lake bed there? What was it geologically that was there that put the sediments in place that you're getting ready to put a 5-story parking garage on for 10,000 automobiles that I may be parking in that may collapse the next earthquake? I kind of need to know that. Okay? It isn't all about just the stiffness of the material, the classification. I forgot to teach people about being geologists first. And that's one of the lessons I want to make sure you guys understand is don't forget our roots. We're geologists. Yes, it may be an SP, but why is that SP even there? Because if it's an old stream channel I'm trying to follow because I want to put water wells in, that's pretty important. Because if I can follow that stream channel, maybe I can find the sweet zone. And so why not play the role of geologist and put in context our classification that we're doing in the field, why we're in the field. So when we come back to write the report, we do a much better job because now we're seeing the bigger picture. And so when I say see the bigger picture, one of the other things my kind of pet peeves is, geologists, we always send our students out to Montana to map the side of a mountain. Okay, well, you can see the whole mountain. There's not a lot of mystery there. Okay, try doing hydrogeology, right? I have a 4-inch boring here. I have another one half a block away, another one a block away from that, and now I'm trying to do cross sections between them. Probably missing a little bit of information, but I'm trying to interpret that. So my outcrop are these little 6-inch borings. And to give you an idea about what I'm talking about, let's put some cross sections up here. Okay? Well, my interpretation is probably not too bad. We could probably put another layer down here. I might have missed it here a little bit, but probably not too bad based upon the area. So do you think I even came close to describing that geology? Nope. I missed a pretty significant area over here, and all of South America I missed. Okay? Now I used to do this where I actually tried to put one right smack in the middle of the ocean. Okay? But nonetheless, really the same information there. We miss a lot of information. And then we only sample once every 20 feet with a 2-foot split spoon. So now, not only do I have very little geology laterally, I have very little geology vertically. And yet I'm trying to make these big decisions based upon it. So don't forget to be a geologist and certainly try to put in context what you're seeing in the field. So location. Now I put this up here because California does not mandate you take a GPS coordinate of your well. Even for the environmental business they don't. Pretty sad. The other thing about California is all well logs are confidential. So you have to go to extreme theft to get the logs. And one of the ways I do that is I work for the water agencies who are the harbor of all the well logs. So the first thing I do when I get a grant with a water agency is I steal all their well logs. So nonetheless, one of the things we can do now with a handheld GPS, which is, like I said, it's less than $100 at Walmart, is we can take that data and plot it on Google Earth. And actually in New Orleans in December at the National Groundwater Association's Expo, I'll be teaching a 2-hour course on how to use Google Earth for water resources work. So here's just an example. Here's downtown Malibu. In downtown Malibu, everybody sits on a septic tank. There is no sewer system in the city of Malibu. So when you see Barbara Streisand's house that sits right here on the beach, right next to her neighbors, all of her sewer water goes right into the beach and right to the ocean. Okay? Well, one of the things I'm doing for the city of Malibu, and actually an ex-student here, is I'm actually out there monitoring all these monitoring wells throughout the area to look at water quality and water level fluctuations. Well, what we do is we come back, we plot it, we have it all already in Google Earth, and we actually put the water levels on here or the water chemistry, and we send it to the city. Really quick and easy. They don't have to have some big, huge reports anytime soon, but this way they can track how things are moving, and we're using Google Earth for free. What's nice about Google Earth is it gives us a worldwide base map. One of the problems we had in GIS and trying to do any kind of mapping is all our base maps are different. They're in different projections. I moved to Michigan. I have to use a UTM, some other measurement over there, or lat-long here and whatnot. Google Earth gives us a worldwide base map that we can plot our data on. And we actually now plot all our geologic surface maps in Google Earth and use that to try and interpret things and actually set it up this way to start with because it gives us some pictures to maybe see what's going on and what's happening. But to be fair to everybody else, Google Earth is not the only one out there. Microsoft has maps.live.com, TerraServer USA, and then for any educators and actually for researchers, Whirlwind 1.4. It's why you have to put in 1.4 to find it, I don't know. But Whirlwind is NASA's version of Google Earth. Now, Google developed it for them, but what's nice about it is all the other satellite imagery worldwide is on it, geocoded and ready for you, and it has all the live meteorological data. So you can track hurricanes across all the different Landsat imagery and some of the other GOES satellite imagery and all the other stuff. So if you're doing work outside the US, Whirlwind is actually a really nice place to start with. Resolution may be a little fuzzy as you go in, but certainly it's a great way to start. And some work I did in Thailand, it really was a savior of some of our resources, water resource work, because we were able to plot faults with it. So remember, we have a professional and ethical obligation to do it right the first time. I think it can help the bottom line because good data collection leads to better business decisions on the project. Then the other thing is, why not, if I'm a water well driller or even an environmental consultant, why not put a Google Earth map together that shows where I've done all my work at? Because if I'm a water well driller in a county and I put in 5,000 wells in that county, why not show everyone where those 5,000 wells are at? Because now the next time someone looks up, they're going to say, hey, that's who I want to hire. And if I'm a consultant, why not make a map that shows where you've worked at? So they can see you as the professional and whatnot. And like I said, you can do this for free, so why not? So let's go into some research. Here's one of the projects I've been working on for several years with the Mojave Water Agency in San Bernardino, California. The Mojave Water Agency is a middle manager in the water business, and they govern or oversee the water resources for a 5,000 square mile area. Basically from the San Bernardino Mountains up the 15 freeway all the way to basically Baker. And then from LA County all the way down to Palm Springs. That is their area of coverage. Now, what I mean by middle managers is they do not sell water to the public. They tax the public, and they tax the water agencies who do sell to the public. And for that, they guarantee that the water will be there for them and the water supplies, and that the water quality will be adequate for the people there. Well, they came to us at the university and said, hey, we have an area out in San Bernardino County, this El Mirage fan here, and this is the Sheep Creek fan that you can see from any satellite imagery. Here's San Bernardino County, which is the largest county in the United States, by the way. It's big. It stretches from Nevada to LA County to Arizona. But anyway, they have this area out here where they have about 500 citizens, and the citizens were having a hard time finding water. One neighbor would drill to 300 feet and have water. The next guy next to him would drill to 300 feet and have no water. The other guy next to him would drill to 100 feet and have water. The next guy next to him would drill to 500 feet and not have any water. Water was just all over the place. It was mixed and matched. Well, geologically, being our geologists, it makes some sense. I have this alluvial fan that's been dumping sediments down here for years and years and years. There's a dry lake bed out here. Intermittent time periods of wetness and dry periods have had this interbed, silts, clays, and gravels, such that it's all over the place. You're going to have perch layers and whatnot. So we knew it was complicated. And we had done some previous, we'd actually did a basin-wide report for them at this point. But they really wanted to go right in here in this little area and really do a very definitive geologic, hydrogeologic model of what's going on right then and there. So the first thing we did is from our original basin-wide report we did for that whole basin, which is called the Oeste Basin, which means West Basin, versus Este, which is the East Basin. I'm trying to learn Spanish as much as I can because everything's Spanish and Indian names. But nonetheless, here we go from the San Bernardino Mountains out into the basin, and you can see out here that we knew there was a lot of clay, and certainly this scale we knew there was a bunch of stuff going on, but we didn't pay attention too much. We also see lots and lots of question marks out here. But the area they really want us to focus in on was happened to be where everyone lives, which is right out here. And so I had a student who basically went into our database, and I want to step back just a second and say, for the first 3 years we worked for the Mojave Water Agency, I had students sitting in front of the computer typing in and scanning well logs. This water agency had, right now I think we're up to 35,000 boring logs and well logs for their area, and they're all paper copies. So the first thing we do is scan them, but the next thing we did is we typed in word for word, misspelling for misspelling, all the information on those logs into a giant database. And the reason for doing this is now it became useful to us. We can actually start doing something with it. Looking at a bunch of paper copies doesn't allow you to do much. So I had my student go in there, and this is an undergraduate student, not even a graduate student. This is strictly an undergraduate project. He went out there and took the 27,000 wells, culled out the 500 or so wells that we found within that little box area, and I had him start going through them and try to take all the different classifications and get them down to something simplified. Now, even within those 500 plus wells, we had tens of thousands of different geologic terms. Okay? So we had to make some decisions. And we had to ultimately get them down into some usable units, and these are the units we actually decided for this particular model. Now, one thing that I started to learn from looking at all these thousands of well logs is that if it was done by a water well guy, almost always he logged it coarser than it really was. Now, we had a bunch of environmental well logs out there because remember Hinckley sits right in the middle of this area, and Hinckley is there in Brockovich, Chrome 6 case. So we had a lot of environmental wells that were drilled and logged by geologists. Well, they typically log things finer than they really are. And I kept going, well, why is that? Then it kind of dawned on me. If I'm a contaminant case or working on a contaminant project, if it's finer, that means it's not going to move very far or very fast. So they want to log things finer. Now, they're not trying to do it purposely, but just kind of in the back of their mind, they're looking for fine grain units. So if you look for it, you're going to find it. Where the water well guys want to find water. They like coarse stuff. So again, they want to look for it. That's what they're going to find. And so we were able to kind of take that interpretation and start making some things with this. The other thing we found out that was kind of interesting is one of the particular well logs we found, my student finally came in and goes, this is exactly the same well log, even though it's for 30 different places. Then we started pulling out the database from this one particular driller, and we found that he had turned in several hundred boring logs from over the 5,000 square mile area that were all identical. The only thing he had changed on it was the name and address. Everything else was the same. So we immediately had to cut those out of the database. So, there's all kinds of issues you come up with. But he was very consistent, exactly. And he can make a good photocopy, obviously, yeah. So here's a map just showing where all those wells are located. And every one of these was a production well for an individual home for the most part. There was 2 contaminated sites in the middle here, so we had some really good geology in the middle. We also got the opportunity to go out and do some boreal geophysics in some of the abandoned wells. So we did some gamma ray logging in those as well to confirm some of the geology. But the first thing you do as a professor is you can't say, jump on the computer and start making a bunch of computer-generated cross-sections. First thing you got to do is do them by hand. So this poor student spent 3 months doing 100 plus cross-sections, both north and south and east and west across this by hand. Okay? And so he did all those by hand and everything, and then we started putting in some of the water levels. Here's some of what our geology looked like. And we started putting some of the water in there and started to see some trends, which we always like to look for. And here's an example of what he ended up with some of these. And we end up starting to see that there are some perched zones and some whatnot. And then and only then, because this student had to be a very computer-generated guy. He loved computers. He was an Apple guy, which even though I only use PCs in my lab, he finally got over that and whatnot. But he really wanted to use some kind of computer technology for his thesis. So I said, sure, let's use RockWorks. Okay, it can build these block diagrams. I don't have much faith in they can do a good job, but let's try it. What the heck? You know, he's done a pretty good job of looking at these. Well, it turns out, here's the cross-section RockWorks came out with, and here's the one he came out with, and they're not too far off. Now, we ran into some problems with RockWorks, and that is, it's trying to interpret both all spatially around you. So it's taking everything around you. And if there's a well that happens to be much deeper than any of the other wells, it's going to draw basically a straight geology across the whole area at that depth. The other thing we ran into a problem with is right over here we have a granite outcrop. Right? There's no water wells in that giant granite rock. So it did not show up in our original RockWorks models because there was no water wells there. So it had alluvium through this whole thing. And so I had to go back and say, let's put some fake wells in there that are solid granite. And so we did that and came up with a better model in the end. So his first cut block diagram looks something like this. But what was nice about RockWorks was pretty easily and quickly we can pull out these little aquifers based upon where people had water and where it's at based upon the geology. We can actually find these perch zones and whatnot and pull them out and say, hey, the people that are in here were all fine. Anybody that was short of that or deeper than that was not fine. These guys over here that are now, their wells are dry, it makes a lot of sense because the little perch system they had was too small to support the 6 or 7 wells that were in that zone without any recharge. So everything started to come together pretty nicely for us. And ultimately, you're able to do some cool graphic things here. But here was his ultimate model they came up with. And it really did pinpoint out where those clay zones are at. And we're able to go back to the water agency and give them some information. And in fact, what they ultimately asked us to do from that model was say, hey, where could we use surface recharge to actually get water into the ground that would reasonably get to the most of the population within the basin? And what we end up with is we end up finding that there are 4 zones here. Now, go back to there again, be a geologist. Is it rocket science to figure out if I'm going to recharge those aquifers, I should not do it out in the middle of the dry lake bed where all the clay and caliche is at? I'm probably going to be on the sides. And of course, there was no mystery there in the end. That's where the best zones in order to get surface recharge into the subsurface was going to be the best fit. Now that 22,000 home development that I started talking about in the beginning, it was scheduled to go right here. So there was also some other need for it. The other thing that's here is the California aqueduct runs right through here. And so it's at a higher elevation so they can siphon water out of the aqueduct for what they're legally allowed to take and put it into a pond very inexpensively. The problem is they don't own this land yet. So now they're trying to figure out whether or not they even need to do it. And at some point in the future, they will have to do it. And this will probably be the area they'll focus in on. And so, and certainly that housing development's not going to go in anytime soon with a housing crash. But someday, somebody may do it. So in the end, we didn't find out anything that was not a mystery, but we were able to describe and actually come up with some reasons why things were happening the way they were. And so we found 4 areas of surface recharge potentially. We understand the geology was very critical to study. In fact, here's that granite outcrop that we modeled right through, so we ended up putting some wells in there to actually force it to show up there. But the computer actually did a much better job than I gave it credit for. I did not expect RockWorks, which is what, $1,500, to give us a pretty darn good geologic model. And yet it actually did a pretty darn good job. So I was impressed, and actually one of the things now we're trying to do is take that RockWorks information, export those layers right into ModFlow, which is the next thing. And so I'm working with, it's right out of Wisconsin, just retired, editor of Groundwater. Mary Anderson. I'm working with Mary Anderson on a paper, not only on the RockWorks side of it, but how we can use it for modeling, because she actually did independently another project and found the same results. She was actually as surprised as I was. So So what can happen new in the future here? Well, as it turns out, logs I see are going to start being uploaded directly to a database in the field. Remember, we have this big, giant 35,000 well database. Well, now as they're out there drilling, they have a laptop sitting there, and they just log right into the database. You know, and they produce a log at the same time, and the data goes right in. Also, the state of New York actually requires you to log on and type in the geology into a database that goes in automatically there. It's the only state that I've found that does that. We're also going to see more 3D visualization. Now, GeoWall, do you guys have a GeoWall here? Anybody know what a GeoWall is? Like, you guys don't have a GeoWall? I figure you guys are state of the art. Yeah, okay. Well, GeoWall is an NSF-funded program to bring 3D graphics to geology in particular. Actually, that's why it's named GeoWall. And what it is, it takes two projectors, put them up on top of each other, and projects things in 3D. And actually, one of the things they have is the molecules for mineralogy, so you can spin them around and go through the mineral and whatnot. But one of the fun things I've seen is you can fly through around Hawaii, underneath the ocean, and actually look at the landslides. Well, one of the things I'm wanting to work on is actually doing groundwater, because there again, we can't see it. So why not take the students to the groundwater and fly them through this model visually in the classroom? The other thing we're going to see is a lot more collection of data in the field. It's just natural progression. We're always going to collect more data. One thing that's going to happen is the drilling rigs themselves are going to start to be computerized. Now, just like your car, when you take it in to be worked on, the first thing they do is they plug it into a computer that tells you, yep, you went too fast and your oil was low. So it's your fault, not ours. Well, the drilling rig companies, for insurance purposes, are starting to do the same thing. They don't want the drilling rigs returned to them because the driller did something stupid in the field. So they're actually going to start putting computer chips in there, measuring down pressure and fluid pressures and whatnot, so they can get a readout when it comes back to the shop. Also allows them to track data. The who controls the data controls the world. So why not have more data so you can make better machines and do more, better drilling in the field? Other thing is field tablets and field PCs. My students go out with a little HP or HPAC, or I think that's what they're called. Has a little menu on there. They click on it. Yes, I took a picture. Yes, I took a GPS coordinates, and this is what it is. Yes, I took a water sample. This is how many volumes I purged. And basically, I have a worksheet for them that I know that they have to fill out before they come back to the lab that tells me everything they did in the field. And then we can actually print that out, put it right in our database, and be happy with it. So we're going to do that. The other thing is we're going to be doing more modeling on the fly. If I can do database uploads in the field, I can change that Rockworks model in the field. It doesn't take very long to run it. So I can actually interpret it and make better interpretation in the field. And then, of course, the GeoWall, which is actually pretty inexpensive, like $3,000 you can build one for a classroom. And it has all free software, so that's the kind of fun thing about it. So with that, I want to thank Franklin Electric for sponsoring me to going around the world here. And also, I want to thank Cal State Fullerton. And I will point out, this is my first furlough day of the semester. So I was not supposed to say anything about Cal State Fullerton, but since I'm here, I'm going to do it anyway. And we're the Tuffy Titans. We have no football team, but one heck of a good baseball team. So with that, I will take questions. Thank you.